Hello everyone. I am Hadi Hajimegi, Professor of Geoenergy, Solid and Fluid Mechanics at TU Delft. And in the next series of videos, I'm going to cover the essential elements of a course that we teach in our master program, which is called Dynamics of Solids and Fluids in the subsurface geoscience environment. And the purpose of doing this course and covering that is that our subsurface reservoirs, the layers, geological layers beneath our feet, all the way to around 5 kilometers under the ground, are covered by a lot of geological layers that are porous. They have pores, interconnected pores. So we can drive fluid flow in them, whether engineering way or natural flow happens there, like subsurface groundwater flow. Or, if we go deeper and deeper and deeper in these geological reservoirs, you get warmer and warmer and warmer environments. And if you find a reservoir with warm water there, you can produce it and extract heat from it. This is called geothermal energy extraction. As you know, also CO2 is a lot emitted in the atmosphere, and we need to capture it at several gigaton scale per year and permanently store it in giant spaces that we can find in these subsurface formations again. So injection and transport of CO2 in these formations would be another scientific topic that we have. Also, renewable energies can be harvested by wind and solar, for example, sources. And then the extra electricity they create can be converted into energy carriers, molecules, green molecules like hydrogen through electrolysis. And then you need to have giant spaces to store the massive amount of hydrogen that you produce with them, so that in the winter time, for example, you can take them back and feed the societies with it. In all aspects, here our main question is, how can we understand flow and transport and mechanics of the subsurface environment, of the geological layers like that? We get a lot of samples from these. For example, this is a rock sample that has coming from one of these wells that we drill in about 2 kilometers. We get a sample and we take them out in order to study them. This is one of them. It's a sandstone rock, and it is the type of a rock that we would like to also analyze and understand in this course. So what is this all about? Let's study this porous material. The first thing that you want to know about a porous material is how much pore volume it contains. So let me draw this here on the board. I have a porous rock or porous material. The first quantity I like to understand about this is how much pore volume it has, so that I can get access to and drive fluid or transport it. That is the measure of porosity. Porosity is the rock property that says that what's the volume of interconnected pores over the total volume of the bulk of the material, total volume. How much of it is pore space that is interconnected so that I can get flow through? This is called porosity effective. Why? Why effective? Because a material can have pore spaces, pores, but they may not be interconnected. So then the total porosity is the volume of all the pores divided by total volume of the bulk. That is total porosity. But that's not really too important for me, because if I cannot access the pores and I cannot have flow through, it's inaccessible space for me. I like to know how much of the pore spaces are interconnected and the flow can happen through. And that's effective porosity. And in this course, we only address effective porosity. And that was just for the sake of completeness. Now, I would like to measure the porosity. I want to understand and quantify it for a specific reservoir I have. How would I do that? How should I report this so that I can represent the effective porosity of this rock sample, for example? Now look at this image of a real porous rock. You see solid grains, crushed solid grains, and the blue space is the water, is the void space, then fluid can be there. Now I would like to understand what's the porosity. How much of this space is porous? If I select a small window, like the box, the white box you see here, and go and measure the porosity, my box is so small that it can be 100% in a rock space, or it can be even 100%, as you see it's moving, in 100% fluid space, because it's too small. So fluctuations of my value of the porosity for the window size, which is very, very small, will be very, very high fluctuations between 0% to 100%, which is 1. So this will be my fluctuations. If I make my box, my window bigger in this space, so it's a bit bigger, you see that the variations as I move forward will be smaller. Which means if I'm entering void space, I am leaving with the other part of my box so that overall the fluctuations will be smaller. If I get it bigger and bigger and bigger, my fluctuations dampen. Which means that if I go from here and I have high fluctuations between 100% to 0%, and my window size gets bigger and bigger and bigger, there is a size over which my fluctuations dampen. This is the representative elementary volume. This minimum volume beyond which I see an average quantity, an average effective quantity. That actually is valid here for porosity, for example, in this experiment, but for fluid physics like density, viscosity, etc., the very same approach we have is valid because we want to report density also in a continuum representative way. So REV is small enough to actually be a point-wise measure of the property, but also big enough to dampen the variations and fluctuations. So this is the scale that I would like to represent my porosity. Now, advanced way of the work is that you may really, in real systems, you may challenge if we have REV at all, when the system is extremely heterogeneous. But let's leave it for the next lectures. Right now we have an REV that allows us to understand effectively what the porosity of this material is. Now, let's now go and measure the porosity of this material at this kind of representative elementary volume scale. How will we do that? This is the definition of the porosity as we covered already. Now, I have my rock sample or my porous medium sample, and I would like to measure or understand the porosity of it. So if I do experimental approach, so experimental methods for porosity. There are many approaches I can have in order to quantify the porosity of this material. One approach is take an image of the surface, a cross section of it. So a cross section can be taken by a 2D image, and with a microscope I can look into this and see the grains as you just observed in my previous slide. So you see the grains, so you understand what parts are solid parts, yeah? And then which parts can be filled with fluid, which means these parts. So here you will measure the volume of the pore space and you divide it over the total volume to get your porosity. But this approach is very uncertain, can be very uncertain, especially if the grain 3D topology and geometry is very complex. Then the cross sections may not well represent your porosity, but that's one approach. Also, you can have a 3D image of it using micro CT or CT scanners. So then you will get a 3D image of the rock at very, very small scale, micro resolution. So there you can get digitally the 3D image using micro CT or CT and then find your porosity by doing image analysis of what are the pore spaces, which ones are grains, etc. What can we do differently? Can we find another way to measure the porosity of a porous medium? Yes, of course. One approach is to find how much a wetting phase, a water, for example, or another like gas, can fill, how much volume of fluid can fill up the pore spaces and be able to measure that volume. For example, I have prepared a sand pack. It's a cylinder, a syringe, which has gauge of volume on it, printed, and I can pour sand to this so that I create a sand box, a sand pack. And I'm wondering what the porosity of this is. This is the simplest possible porous material you can create in order to study at home these kind of concepts. Now, what is the porosity of this sample? So, let's do this. I want to know how much pore space here this sand pack has. Imagine I have another syringe with a gauge of water and I can add a certain amount of water in it that I know how much of. For example, 15 or 10 milliliters of water can be injected here. I'm just injecting as I'm speaking with you. And then, as I inject water here, I need to shake this sample so that air bubbles are released and water penetrates this sample fully. And then at the end, what I get from this sample is very, very interesting. Is that I have a rock sample, which is this sample. So I'm going to the measurement experimentally. I put my sample of sand pack in this syringe, which initially had a volume of the bulk, like VB. Then I added water to this system. So I added water with a known value of the volume. And the water went inside the pores, filled it up. I shaked it also with my fingers. And then I actually got more water on top of this as well. So the water that was extra came to the final gauge of V, for example, A. It's just a number, doesn't matter. So I added total amount of water volume. It went inside my pore sample, so it filled up the pore volume, but it also gave me an extra volume, delta V. And that is exactly the volume at the gauge A minus the volume at gauge B bulk. And I can read this in my syringe. And I can read the total volume because it's the second syringe I use to fill up the other one. This gives me a very simple approach to know my pore volume, which is the total water volume minus the delta V, the extra water level that is here. And if I know that, then the porosity will be very simply found as V of pore volume divided the bulk volume, which is the total volume, or VB. That's very simple. The challenge is, I cannot do that for this very simply in the atmospheric pressure. How would I be able to do that? I can do, as I said, 2D image, I can do 3D image by micro CT, or I can actually try to do another approach using thermodynamics. How would I do that? So, let's look at this. Let's see how I can find the porosity using thermodynamics law. How? I am going to create two-chamber system. This is the first chamber, the second chamber, and then I have this. There are two valves here that I can switch on and off. I have the chamber 1 with a known volume and chamber 2 with its own volume. These chambers have pressure gauge, so I can read the pressure of them whenever I want. So pressure can be read. At the first beginning, I am going to place my rock sample in chamber 1. This is my rock. So when I flow in my helium, my air at low pressure, I know that my gas is first contained in the first chamber part. So I take the volume of stage 1 of my gas, times the pressure P1, V1 is the pressure volume of the first stage of my gas. If I open the other valve at constant temperature, so keeping the temperature of the system constant, my second pressure will be P2, so I'm opening the second valve, closing the first one, and then the gas spreads all over and fill up the other chamber. The pressure drops naturally because gas is now expanding itself to fill up the other spaces, and I'm keeping the temperature constant. So P2 is known because the gauge gives me the pressure, and then the volume of the second stage of the fluid, of the gas, will be the second volume. PV is constant due to gas law when I keep temperature constant and assume that the system follows nearly ideal gas. So, what will happen? I can measure P1, I read it from the gauges, P1, P2, but what are P1 and P2s? I'm sorry, V1 and V2, volume 1 and 2. P1 is known. Volume 1 is the volume of the chamber 1 minus the volume of the solid rock, the grains, because grains are solid. They don't let air come in, but the space between them, the pore space, will be filled with gas. The stage second is the P2, which is known to be, and the volume 2 is when I open the second valve and close the first one. So this is closed, the other one is open, and the gas flows all over the space. Which means that it will be the volume 1, which is volume chamber 1 minus volume solid, plus volume of the chamber 2 fully. This is volume of gas 1 in the stage 1. So chamber 2 is void, fully available for the gas to flow through. Fantastic. So in this way, I can measure the volume of solid because I know P1, I know VC1, I know P2, I know VC1 as I said, and I know VC2 because this is chamber 1 and chamber 2 volumes are known to me. So this way, I can find the volume of solid. And when I know the volume of solid, I will know the volume of the pore space of my rock is the total bulk volume of my rock minus the solid volume, the grains volume. And there I can find the porosity to be volume of the pores divided by the total bulk volume. Fantastic. This is gas law, which is extremely convenient for me to analyze, understand. If I have these chambers, obviously I need to fabricate the system well that, for example, the volume of these parts in my pipes, etc., are considered properly too, or I make them extremely narrow. Now, this is a great way to understand and measure porosity, which is based on thermodynamic law. You can have many other ways to calculate your porosity. For example, you can know, if you know the density of the grains that form this rock, and you know the weight of this rock, then you know if it was 100% solid, what would have been the volume of it, right? We know the mass. If you know the mass, you know that divided by volume is density. So if you know the density, and then you know the mass of this system, you should know then if it was 100% grain, only solid, what would have been the volume of it? And now you know, but the volume is bigger than that volume. Why? Because those are empty spaces. And so it gives you the understanding of the void volume that you have, the pore volume that you have in this rock. So density and measuring the weight of it could be also used for understanding the porosity. There are more approaches that you can use as well. You can take a tank of water, put your dry rock, you know there is a dry rock, so I have dry rock sample, and then I have fully wet rock because I put, for example, this rock inside my water. This is filled with water, so there is water everywhere here. So it's water tank, and my rock comes here and gets fully wet with water. So it gets fully wet with water. When I bring it back, it's fully wet rock. So fully wet rock. And if I measure the change of the weight of this, I know the change is only the representative of the weight of water, because water has filled in the pore spaces. And if I know the density of water, then I know what's the volume of water that is there, because density is mass divided by volume of water. So if I know what's the mass of the water in by measuring the mass before and after, I know how much heavier it became, then I know the change of the mass, or delta M, and then this allows me understand what's the pore space that I have, because water is filling my pore spaces, and I know density of water, the temperature and pressure that I'm doing this experiment. See how many ways, creative ways you can have to understand porosity. Why does it matter to us? Because it gives us the capacity understanding of how much pore space my reservoir has. If I go to the surface and go down to reach my reservoir, if I know the total volume of my reservoir by the geophysical surveys, I can find, with the knowledge of porosity, how much pore space my reservoir has, and that gives me the total capacity of it, and how much fluid it can contain, or how much fluid it will eventually be there in the system. And that's actually a great understanding of what would be the capacity, for example, for CO2 storage, or for hydrogen storage, or if I have warm water, how much warm water I have, so how much energy I can extract from this reservoir. This gives me that capacity. There is one important fact. porosity is heterogeneous. It changes its value across my reservoir. So porosity will be very different in different locations. You can have small, low values, you can have large values. And that's the geological heterogeneity, that rocks are different types. So you can have a rock that is like this, a sandstone rock, that might have 20%, 25%, or 30% porosity. You can have very, very, very hard rock or shale formations that would have very, very low porosity. So porosity is very heterogeneous. And so you need to calculate the porosity times the volume of element, and sum them all up in order to understand the total void volume that you have, or pore volume you have in your reservoir. Importantly, porosity changes as you inject fluid or produce something out. Fluctuating pore pressure inside your reservoir deforms your reservoir, and as a result, your volumetric strain will impact the porosity of your reservoir. So you inject pore fluid, you make the pressure high, you may get higher values for the porosity. You may produce fluid out, you cause more compaction in the reservoir, you may lose your porosity. Porosity is a lattice space, pore space that you have in your grains, between the grains that you have this pore space, and they are also flexible in terms of mechanical information too. This is the entire topic related to porosity, and next we move on to permeability. Thank you a lot for your attention, and I hope it was